Hi, everyone, and welcome to our webinar introducing a new era of integrated lasers. This is the 12th in a series of webinars presented by COBO, the Consortium for Onboard Optics, and sponsored by DuPont's Silicon Valley Technology Center. Our webinar today is going to last for 1 hour. First, we'll hear from Jeffery Maki, who is a distinguished engineer at Juniper Networks and a director of COBO. He'll be giving us an overview of the possibilities for integrated lasers in pluggable, co-packaged, or onboard optics data center applications. Then, and because we've titled this a new era for integrated lasers, we're going to hear from a new player on the scene, OpenLight. And we have with us today Dr. Tom Mader, who is COO of OpenLight, which is the newly formed joint venture company between Juniper Networks and Synopsys that's working with Tower Semiconductor to bring this technology to market on a scalable platform. And then finally, you're going to hear from Yuval Shay, who's Director of Product Marketing at Synopsys, who'll be discussing the toolsets and design methodologies available for developing applications on these platforms. So your questions are definitely welcome during this presentation. Please use the Q&A function that you see below. We'll have time at the end of the presentations for going through those questions. And if you could please direct the questions or just type in your question, whether it should be directed to Jeff or Tom or Yuval, that would be great. And so with that, let's kick it off and get started. Jeff, the floor is all yours.
All right, thank you. Let me share my presentation. So the data center front panel and embedded I/O, I wanted to review in a few slides. So this is a pictorial summary. Some of you may have seen this over the years. I always keep updating it. This is going from 400 gig on the left all the way to 1.6 terabit on the right. So in the 400 gig generation, there was a lot of activity in the early days where it was thought the industry would adopt 400 gig Ethernet using 25 gig electrical lanes or SerDes. But that really didn't take off, although we spent a lot of time on it. But what happened is we really focused on these 8-lane form factors, and in particular the OSFP, QSFP, DD, and COBO. We had these 3 modules developed, and those were what really helped them to get 400 Ethernet moving in the industry. Now, when we go to the 800 gig generation, we see that being updated now with a lot of focus on OSFP and QSFP DD800. So this has been the form factor evolution so far. Of course, there's still other contenders. Even now, this 16-lane CFP8 modules still in consideration. And I've heard now even some people are taking CFP8 to 1.6 terabit. I don't want to focus on that, but I just point out it's a 16-lane form factor. And at the time, people said, well, that's why it didn't take off, because it was 16-lane. Well, we'll come back to that on the next slide. So we're here in the middle of this 1.6 terabit generation. In particular, now we have the OSFP XD form factor, a 16-lane version of the OSFP module in a sense, although OSFP XD is completely revamped and its own separate form factor. So that's creating a lot of excitement in the industry for this next generation of front panel pluggable form factor. But we still have now the COBO onboard optic form factor. Moving to the next slide, then we have this outlook now to the 3.2 terabit generation, where we have the OIF co-packaged optic form factor, which I've shown here, a picture, top view of it. And these relative size are all correct. So the OIF CPO is a 32 lane module to achieve the 8 ports of 400 gig Ethernet using 100 gig electrical lanes. But now we have Also the OSFP XD, as I said, is 16 lane, being projected for use with 200 gig lanes, and Kobo with its 16 lane module is also a contender in this area. So this last slide to show you is these roadmaps in the industry. The blue line shows the single lane form factor that is well known, the SFP, and it keeps progressing to higher speed electrical lanes. Then the red line is this SFP-DD, which is seeing some adoption, but it's a 2-lane module. And then the purple line is a very favorite module in the industry, the 4-lane QSFP, and it keeps progressing to higher speed electrical lanes. And then we spoke a lot already about QSFP-DD and OSFP. But now here in the upper right corner, we have the 51.2 terabit generation with 100 gig electrical lanes in the OSFP XD form factor as a possibility, or the OIF CPO as an opportunity for such a system build out. And now in the far upper corner, we go to 200 gig. We can project now to even 102.4 terabit 1RU line card using front panel pluggables. So quite an exciting roadmap here. Now we need to fill it out with technology to make these modules. So I turn the talk over now to our next presenter, who'll talk about, in a sense, the optics on the inside.
All right. Hello, everybody. Introducing OpenLight. So we're here to drive the next era of open silicon photonics with integrated lasers. I'm Tom Mader, as we mentioned, the COO at OpenLight. So OpenLight is a new independent company. We are providing the world's first open foundry volume silicon photonics platform with integrated lasers, where it is actually offered through Tower Semiconductor. So Tower is our beloved partner that is offering this, and it's under license from us. So just to be clear, you go to Tower to go access this. The platform today, and over time we do hope to have other foundries and spread it wide. We call ourselves OpenLight for two reasons. One is we want to bring this to the world, and we'd like it to be open to however people want to use it. The platform does address growing photonic applications such as datacom, telecom, LiDAR, healthcare, high-performance computing, AI, and optical computing. And I'll mention it again later, but we have many customers coming to Tower and to us directly from all of these. The OpenLight technology provides a new level of laser integration that delivers scale and performance to we believe will accelerate new applications. And this is a bit of what's been called a holy grail in the industry. We are not the first to have this technology in volume. I think many people know that Intel has a technology like this. They've been shipping in volume. We believe we are the first to have an open platform with a PDK offering on a volume platform. So, and it's always good to have more than one doing a technology that brings credibility to what we're doing in some ways. So technology, we passed the reliability tests. We're ready to go on Tower. And so Tower is offering MPWs. We've already taped out the first one. There's another one going out later this fall. And finally, OpenLight was formed with investments from Synopsys and Juniper. So we were previously part of Juniper. I was part of the CTO organization, reporting to the CTO. Now we are an independent company, majority owned by Synopsys, minority owned by Juniper. So this is addressing the laser integration challenge. A key challenge for silicon photonics. Silicon photonics is wonderful because it goes from completely discrete devices to an integrated platform that has modulators, photodetectors, routing, et cetera, and all kinds of passive elements, but it's been missing the laser until recently. And so we now bring the laser on board, and it does address the cost of the discrete laser and the cost and manufacturing challenge of attaching those and aligning those. Our open platform includes integrated lasers, optical amplifiers, and other key photonic components, such as a low-loss modulator. And we end up focusing a lot on the laser. The laser is very important, and it allows scale. But over time, we knew, but are being being confirmed with our customer interactions. Optical amplifiers are also very important, in particular for some of the arenas such as LiDAR and sensing. You can re-amplify across your chip, and it's for the more complex chips in a lot of the areas. The optical amplifier is actually a key differentiator, particularly with the low loss in and out of the amplifier. We have only a few tenths of a dB loss from the amplifier or the laser. And I will mention the modulator. We have an electroabsorption modulator, which is a bit unique. And a couple of the key things there is it's, first of all, very small. And second of all, it goes to high speeds. So we are already working on a 200 gigabit version, and it scales more easily to 200 gigabits and so the very high speeds than we think some of the other types of modulators do. And finally, but very importantly, we have only 1 dB of excess loss in our modulator. That is a really big deal. And that speaks to some of the power advantages we believe we will have over time. But we also believe that the technology will bring advantages to co-packaging applications. And so I'll move on. I just mentioned here, these are discrete elements. This is just an example of our PIC here that's on a substrate. And this is actually a photograph of a program that we were doing previously that was a 400 gigabit PIC that was transmit and receive all in one. So this is an example. This was a program we were doing previously. It is a 400G PIC. You can see the 100G PAM4 eyes on the upper right-hand corner, and we were demonstrating a good margin on those eyes, which we were pleased to see. And you can see that we in this program we had the PIC here flip chipped down, and you can see the breakout of the bottom of the chip here, where you can see the electroabsorption modulators, you can see the lasers, you can see the photodetectors, etc. And we had everything here, including a control and microcontroller. This was basically a transceiver on a little substrate. So it kind of gives you an idea of what it looks like in an example application. Okay. The OpenLight technology does bring integrated lasers, and as we mentioned, optical amplification and a very low loss, high speed modulator to a broad array of applications and packaging. The key here, I would say, is that we believe that we are a good technology and, in fact, an enabler for some of the next generation optical interfaces, doing deep co-packaging, but as well as co-packaged optics. But we're also very happy to serve the pluggable market. And in fact, if you prefer an external laser, this technology can actually be used to make the external laser. So we are agnostic to how it's used. We would like it to be used any way you would like to use it. That's why we call ourselves OpenLight. But we believe that we will have some advantages in the next generation as things shrink. And we also believe we have advantages in the pluggable space. We know the datacom arena the best. We came from Juniper, and we believe there's a good market there for us, and we're very engaged with customers there. But we're getting a lot of interest from LiDAR companies. We have quite a few, particularly in the coherent space, and we believe we have a very nice advantage there, particularly with the optical amplifier, and in particular developing a high power optical amplifier. There will be applications over time in telecom, also in what we call, inter GPU interconnects. That is one we believe we have a very nice play there, and we have some customers we're engaging with to apply to that. And then finally, there's health. There are some medical applications where we've had some interest, and there is the other things such as optical computing, where we have some customers coming to us, which we're very excited to serve. The OpenLight process design kit, this is available. You can go to Tower and you can access it. It is here now. We just taped out again the first MPW, and there's another one coming, I believe November, but Tower can speak to that. We have a complete platform of passive and active devices. So in the middle of the page here, you see the passives, and it's all of the classic things: waveguides, splitters, filters, etc. And on the I/O, we have the top coupling, both for wafer test and as well as for I/O, but we also have an edge coupled solution that you can utilize. So on the left-hand side, you see the tunable laser, the optical amplifier, the modulator, photodetectors. Everything you need is here. We, again, believe this eliminates barriers to entry, very low loss between the components. And I will mention, not to steal any of Yuval's thunder, but the PDK GA, our first GA, is going to be in September. It's coming literally in the next couple of weeks, and that will be interesting for everyone to have. It has some really cool features that we believe will enable our customers in a new way. In passing, I will mention, this is a very wide audience. If you want more detail on this, or if you want to see our roadmap, of course, come to us and we can, under NDA, tell you more. I will say we are actively working on a DFB. We have a 200 gigabit modulator. There's several things in the works, and we're very excited about it. Okay, OpenLight PIC design solutions. This is something we didn't set out to. We're not selling PICs. That is not our business. We offer a PDK, and we would like you to design your solutions here to do anything you'd like to do. However, we've found that to accelerate the market, we have done some designs, and we actually have a 400 gigabit DR4 transmit PIC, an 800G DR transmit PIC with 2 kilometer reach. We have those samples available now. If reach out to us for it. And coming soon, we are working on an FR4 that's actually in fab. We have 2x-FR4 and 4x-FR4 in the works. And we believe that for 2x-FR4 and 4x-FR4, that we begin to have a more radical advantage. We believe we can fit into these modules, the QSFPs with the 2x and OSFP with the 4x. And we also have an 8x200G PIC design at 1.6 terabit. So again, we're very excited. Come talk to us. We'd love to talk to you if you have an application. And we are engaged with many customers already across key areas, primarily data center, but also a lot of engagement on LiDAR and some in these others, the optical computing and high performance computing. And this is, again, a photograph of the bottom of one of the PICs we did previously. So in summary, OpenLight, we are a new independent company. We're providing what we believe is the world's first open silicon photonics platform with integrated lasers on Tower's platform. We're very happy to be partnered with Tower, and you can go to Tower or us if you want to start. It addresses multiple applications: datacom, telecom, LiDAR, healthcare, high performance computing, optical computing, you name it, and perhaps some that we don't know yet. So it's a very exciting time. Just for 1 second, I'm gonna pause and talk about our advantages. And in this order, we believe scale, speed, power, cost. And scale means you can do a 4x-FR4 on a chip. Over time, you can do that at 200G per lane. So scale and actually size, speed, and then power consumption. And power consumption with a DFB and an electroabsorption modulator with only 1 dB of loss and a few tenths of a dB loss between those elements, it becomes hard to beat. And so we are very excited about it, and we'd love to talk to all of you if you'd like. And of course, cost at scale in particular. As this ramps, we believe this is the way to get there. So it was developed on a proven technology. We have over 200 patents in total on both device design and process integration. And again, through Tower, our partners at Tower, our next MPW is scheduled in the fall. I believe it's November. And of course, we also have the very deep partnership with Synopsys, and we are excited about what we are doing with them on the tools. And that I will turn over to Yuval.
Right, let me share my screen now. All right, thank you so much. So thank you everybody for joining us today. I'm very excited to talk to you. It's my first time in this forum on this panel, so take it easy on me. If Jeff was talking about the end application of what you do with all those great technologies, and if Tom was talking about the process, the technologies, the device physics, what they are offering in terms of a platform, I will be kind of in between. How can we take those elements? How we introduce those technologies to engineers so they can take it into a design platform, put it all together, and design wonderful things with the software and with the solution that we have. That's what I will try to cover here. But before I do so, just a quick few words on who we are in Synopsys. So we have a broad portfolio of products and solutions, all the way from silicon design with the TCAD and lithography, a type of products and tools that we offer to foundries and others, to design tools that are going from analog to RF, mixed signal, and of course, digital designs, all the way to the system for hardware and software verification and prototyping, so people can really test how the software will behave on the products that they are just designing before it even goes to the fab. So really checking how the software designed by itself. And we are also offering a broad portfolio of IP. We are #1 in interface IP, SerDes and high-speed interfaces that we have. We have also foundations and other physical IPs. And at the top of this solution, we have software solution for application security testing and quality of software design. So we are really offering a broad and comprehensive set of technologies from silicon all the way to software. Since today we're talking about more on the photonics and the optic side of things, I just want to mention that for Synopsys, we've been investing, or we saw the light, pun intended, for quite some time, over a decade of investment through acquisitions that were made, a lot of organic development, a lot of innovation and integrations of tools that we created or we collected along the way to create really a robust end-to-end solution, all the way from the silicon photonics and all the way to the optics for those who needs all of that. And you can see just some of those tools and capabilities that we have on that slide. But today I will focus more on photonics, and I want to just mention, because we are talking specifically here to datacom type of audience, we see the trends of more and more photonics and PIC design that are happening. If it started with pluggable when that was mentioned earlier, to onboard optics, and what we see today is a lot more integration into the a co-package in a 3D chiplet designs, where lasers are being integrated into those silicon photonics chiplets or chips, and we see great adoptions of silicon photonics platforms in a variety of applications, from datacom to compute to quantum computers to sensing to LiDARs. So it's not just limited to the transceiver markets or to the telecom market, but we see a lot of interest and a lot of innovations, many startups and many big companies that are investing in silicon photonics. Tom mentioned a few earlier, I will not repeat, but it really looks like we are in that stage where that becomes a lot more mainstream. So what do we offer in that space? We want to make sure that when the market is ready to start really innovate in silicon photonics, we are ready with our software, and we have quite a bit of capabilities, and our solution spans from all the way from the device creation itself, and these are tools that Tom and his team are actually taking advantage of, creating those devices, creating models for those components, the photonic components, creating different views for later on be able to use them in the design platform. We have a variety of capabilities from TCAD all the way to modeling capabilities that we are offering in the component level side of the solution. We are also have our simulation capabilities that creates both, we provide both circuit simulation capabilities for optical, electro-optical simulation, but also we are offering a system analysis or system architecture tool where you want to really see how a transceiver goes through a fiber, go over 2 kilometers of fiber to another transceiver on the other end, and you really want to measure that entire performance across the system. We have solutions for that. But where I will focus a little bit more today in the next few slides is really the design platforms. How do we enable engineers taking what physicists like Tom and his team are taking the components that they are developing and put it in a form where photonics IC engineers can use in a design platform that give them all the capabilities that they need, and I will cover those in a minute. But before I will talk about the design platform itself, well, I'll just talk about the enablement, because this is the most important and crucial piece of making it all work. We somehow need to bridge, as I mentioned earlier, between those physicists and the device physics to the engineers, and we do it with those process design kits. And we are collaborating with all the foundries that in the space, in the photonics and in the photonics space. We are working, of course, very, very closely with OpenLight, and we are working very closely also with Tower. You could see some of those press releases we did lately on enabling photonics platforms across different foundries. And what the PDK, the process design kits, is providing is, an array of components, photonics components, and in some other cases, it's mixed signal and analog and photonics components with simulation models, with the design rules, with the LVS or physical verification capabilities. We are working with on reference flows with those foundries and with OpenLight. So when engineers are ready to take on those platforms and start designing, they have all the ingredients that they need in order to put together those designs, which I'm showing here, one of those examples on the right-hand side. So let's talk about the photonics IC design platform itself in the next few slides. What we wanted to make sure we accomplish here is that we provide the same tool look and feel to engineers who are doing mixed signal designs, right? They need a schematic capturing environment. So we, under the OptoCompiler solution, we have a schematic capturing environment where all those components that the foundries are providing can be instantiated, put together, do all the design. Of course, we have a very robust and capable layout environment with a lot of automation and the core capabilities of curved linear shape support that are very, very much needed here. And I will show some other capabilities that we have. And we are tying it all up with a simulation environment that enables running simulation in an optic simulation by itself or electro-optic simulation when it's needed. And that also provide access to tools for the analysis of those simulations with the specific analysis capabilities for the photonics community and what they need. So this is kind of in a nutshell, in a high level of what is OptoCompiler and what it provides. I will show just a couple of examples, actually 3 examples of the productivity and the layout automation features that we have. Table stakes items like on the left-hand side where you can see we have perfect abutment when you put together 2 waveguides and you want to make sure that they are perfectly abutted, no gaps, no breaks in the waveguide shapes. We make sure that if the ports are matching and we are actually also annotating all that information on the layout. You can see on the right-hand side some placement automation and automatic alignment capabilities that we have, where we are saving a lot of time for the photonic engineer, how to put together the entire design in layout. And one of the great innovations that we have developed in the area of interactive waveguide routing or what we call the flexible connectors. You could see in the bottom side of the screen how we are enabling a photonic engineer to take a bus of connectors, connect them very, very rapidly, very, very quickly, able to reshape them, change the topologies there. And all of those changes that are happening in the layout will automatically get back annotated to the schematic. So all those changes that were made can be now resimulated to make sure that everything is still in check. We also introduced some capabilities there to make sure that all those connectors are in a constant delay between each other or zero delay between each other, just to make sure that the photonic engineer really able to implement exactly what they intended to implement. So in summary, for the photonics solution, we have really a robust, unified electronics and photonics platform. So the same platform that I was mentioning a second ago, the optocompiler, also bring capabilities for mixed signal design. So in cases where people are using photonic engineer needs to have the capabilities of both mixed signal design and photonics all in the same platform. This is what we are offering here. Robust simulation capabilities for optical simulation, for electro-optical simulation, ability to close really fast the physical verification, really have some innovation there with our IC validator tools that is tightly integrated into our photonics solution. And as I mentioned earlier, for those who need to create their own photonics components, we see it all the time where what the foundry is providing is great and fantastic and they take advantage of it. But our engineers tend to create their own unique components. So we have our photonics device compiler and our TCAD capabilities that we have there for them to be able to bring their own components. And of course, we are closing all of this with robust simulation capabilities and layout capabilities that really accelerate the design and with a faster layout and faster turnaround time. So with that, this is kind of a brief overview of what Synopsys are offering for silicon photonics engineers. If you want to hear more, if you want to talk to us, we will be delighted to. Please reach out to us. And if you want to see a demo, or if you want to test drive the tools, we will be more than happy to work with you on all of that. And with that, I will turn it back to Jim. So thank you so much for listening.
All right. Thank you, Yuval and Tom and Jeff. Great presentations. So we have about 25 minutes for Q&A here, and we're starting to see some of those questions come in right now. So I'll be reading off those questions to our panelists here. I'll do so anonymously. So please continue to use that Q&A function, and we'll get to as many of these questions as we can. So as we get going here, Tom, could you give us first a little bit more on the backstory of OpenLight? How long have you guys been at this?
Yeah, it's a really good question. The company has an interesting history, and it came originally out of technology from UCSB, John Bauer's group, formed as a startup in the 2000s, was acquired by Juniper in, I think it was 2016. And has now turned into this. And as people know, silicon photonics, and particularly this kind of technology, it's hard, right? And it takes some time. But we're at that point now where we're just ready to ramp. So yeah, it's and many of the team members have been at the company for more than 10 years. So there's a lot of deep expertise here.
Okay, and same for Yuval then. How long have you guys been working on this kind of photonic integration, and any work previously done with Tower?
Yeah, well, we are working very, very closely with Tower. I mean, we've been working with Tower before photonics came to be, and we've been working with them when they first created their platform for silicon photonics. Very day-to-day working relationship. I must say, we are helping them with tuning the PDKs. We are collaborating in a three-way with Tom and his team to make sure that the end users will get the state-of-the-art or best-in-class or whatever they need to do from the PDK aspects. So the working relationship is phenomenal, to be honest, and very rewarding. I will not name names because I did not get I did not ask them if they want to be named, but it's a very good collaboration on the tools, on the qualifications of the tools, on making sure that we are ready when our engineers, end users will be ready. All of this is happening all the time.
Okay, all right, great. And Jeff, how does this technology change the picture for Kobo?
Kobo, we're here to foster innovation and drive the industry forward. So I think having technologies that can help to answer the question of cost and power are very important, and perhaps give new answers to cost and power from our historical choices of technology. I overviewed in the slides, we know what the size needs to be. Kind of know the size, but what we need now is innovation on cost and power reduction. And I think that's the opportunity being examined here, and Kobo's here to try to bring that forward.
All right. So I think a lot of the questions that are coming in are going to be about the manufacturability and perhaps the intellectual property, the relation between the different parties here. So let's take the first one, and I think this one probably goes to you, Tom. How much of the process is from Tower, and what is the role of OpenLight?
Well, to clarify, it is, Tower is fabricating the process, and we worked to show them how to do the part of the process. Tower knew how to do silicon photonics, and as many here on the call know, they have a robust silicon photonics line, as silicon-only silicon photonics. We added bonding indium phosphide and then creating all of these indium phosphide elements and processing them. And in exchange for showing Tower how to do that, we do a license royalty model where we are, presumably you could argue we're in the background, and you go to Tower, just use this process. And then there's a royalty and license model that we have with them. It's a little bit like ARM or that type of a model. Does that make sense? Yeah, so it's Tower's process under license from us.
Okay, and I think you mentioned that you would be open to working with other foundries.
Yeah, we again, as OpenLight, we like everybody to use this. We'd also like to bring it to everywhere that can find advantage to the platform. Yes. Okay,
I think in one of your slides, if you wouldn't mind bringing that up, slide 6, you were talking about the silicon photonic passives in there, and there were different blocks. And I was curious if those are kind of the IP from OpenLight or from Synopsys or from Tower, the various things there, whether ring resonators or the waveguides, those kind of things. Are those different blocks that a customer then would choose and license as part of this kit?
Yeah, and essentially all of it is we are doing, think of it as we're doing tape outs, both passives and actives. We have models of those, and then we test them. And we then work very closely with Tower. We have a great relationship, as you've all said, between Synopsys and OpenLight and Tower. And again, we have other relationships too, but that trio is a very healthy one. We're very friendly. We generally, a lot of times, it can be a lead customer, whoever that works on a PDK. We're simply making sure that all of those, that we have test data connecting to the models. we work closely with Synopsys to have the tools where the models, we have a good collaboration there. But again, we bring those then to Tower, and we did that on the passives and the actives. And so we are developing those models together with Synopsys and other tools. And so, yeah, I mean, we do literally tape out these parts, model them, test them, make sure it resolves, and then have a PDK element to hand over, if you will.
Okay, and Yuval, then your tools then match in with all of this.
So in the end of the day, what the way the PDK looks like is exactly what Tom was saying. They create all those components. They provide a variety of views, whether it's simulation views, symbolic views for schematic, layout, parameterized layout views, so people can take advantage of it. And they package it in those PDKs, and it automatically appears in the design platform itself when it's all being loaded. The tools are developed with all those notions in mind, or all those parameterization that are needed in mind. So we make sure that everything that the circuit engineer will need to implement in the end of the day, we can take it, we can manipulate it the way the engineer needs to be manipulated, whether placed or in different angles or in any way, or abutted, or there are some other parameters that needs to be used, and we make sure that the tools are ready for leveraging those components. And I also, as I said, we are also enabling our end users to expand, or enhance their library of components when they need to do so. We don't see it much in the active components. Lasers are proprietary. This is what Tom brings to the table, not only the laser, but a lot of those active components are kind of the IP. But we do see people innovating in how they want to do their connectors, and how they want the waveguides, the splitters, and things like that. We see a lot of end users or customers who wants to bring their own little piece of IP into the mix, and that's what this is all part of the capabilities that both the PDK provides, because it provides all this process information that are needed for that, and the tool provides because we provide the tooling that can implement those. I don't know if I answered exactly the question, but okay.
Okay, all right, good. So Tom, you showed some examples then, so the picks, right? But your comment was that you're not necessarily going to be making that 400 gig pick yourselves?
Yeah, you mean like this one where we?
Yeah, this one, and then there was the 400. There was a slide I think that had the 400 gig pick on it.
Yeah, we also had the 400G, for instance. You're talking about this guy.
Yeah,
yeah, and we had a model of doing it ourselves prior, and then we decided to switch to this business model. Again, we offer the PDK, and you say, well, when we did also mention that we are doing pick layout designs ourselves. We're doing that to seed the market in areas where there's a standard and where we believe we can get customers there faster. Again, this is a design we say, here you go, this saves you some time. For instance, on the DR800, some of the 2xFR, those that we just see an opportunity to shortcut for several customers. There is a model like that in the electronics market, right? I mean, people do have SerDes cores that are GDS ready in the industry. So it's not something that's unique in the electronics space, but it's all about whatever we can do to make customers move faster and enable them to get to market.
And so those would be offered kind of as an OEM basis to other
it's
vendors.
design, and you're still buying wafers from Tower, right? So it's you're not buying picks from us.
Okay.
How we're modeled, yeah.
Okay. So a couple of questions in here also on the manufacturability then. And I think this is where you may start to see the first yield numbers and things like that. Is that right? Could you comment on yield and the overall manufacturing process?
Yeah. Again, this is a very broad forum, and we're not under any NDA, but in general, what I will say is us and Tower, who, like I said, we meet with them every week, meet with their SVP monthly. We have a great relationship there. We are very bullish on, again, the reliability looks really good, but the yields are looking good. I don't want to share numbers because, again, this is a very open forum, but it's actually some of the latest of the DR800. The yields were actually better than we'd expected. So we're very confident that we're going to get quite good yields. And we, again, that's not actually one of my primary concerns, to be honest. You always track what are your top 3 risks. It's not one of them. I actually feel quite positive, quite good about it.
Okay. And same thing with some of the other numbers that you cited, like for the loss and the modulator, you would expect that to be like a benchmark number that other designs using that would also deliver?
Yeah. And one way to look at that is, this is probably one of the absolute key things, the loss from indium phosphide to the silicon waveguide. I can't give you an exact number. There's a distribution, but it's on the order of a small number of tenths of dB. It's a few percent, which is absolutely revolutionary, right? Because it enables you to have a modulator that has an excess loss less than a dB, which again is pretty revolutionary. It gives you, if you have, when we have our DFB, which is on the roadmap, it's right into the waveguide, right? And the optical amplifier, you have low noise. So that's I won't give you an exact number, but I'll say it's on that order. And with large volumes, you can put 100 of these on a pick. You're going to see something with a distribution around that. So.
Oh, okay, interesting. It's a pretty large number. And is that for reliability reasons that you would put that, or you're just trying to achieve density?
You mean to put a lot of elements on a chip?
Yeah.
That's so you can do a 64-lane LiDAR or the Kobo 8x FR4. I think that's about 64 lanes, 8 times 4, 32 lanes. So no, the reason you put a lot of elements is simply to get higher density applications.
Okay.
Yeah.
Okay. So there's a question, you referred to hybrid laser. Is this the same lasing in silicon similar to what Intel has been doing?
It's a good question. It is analogous. I believe that these both came out of UCSB. We are quite different. Our 200 patents, so to speak. There are some differences in how our mode is relative to Intel's. So it's analogous but different. So.
Okay. Another specific question. What's the total power of the module? I'm not sure which module is being referred to there, but.
Yeah. Thanks for the question. Specific numbers, we can come to us. We can do an NDA if you have a business engagement. I would say in general, the DR800, for instance, that we have that pick, it is competitive. It is as good as the best out there today. Once we have our DFB, which is coming soon, we start to pull ahead, and we believe we're going to be below what some of the competitive offerings are on the FR and the DR offerings. All
right, great. Tom, we've got you on the hot seat here. Can you elaborate more on the EAM specifications? How much is the loss to couple the light from the EAM to the SIP pick and from the laser to the EAM? Also, what's the swing requirement?
Well, this may turn into if we come to us, we'll talk. Again, when we talk about a few tenths of a dB, it's from the laser into the waveguide and then up into the EAM and then back into the waveguide, right? So when we say it's a 1 dB excess loss of the EAM, that's in the waveguide, that 1 dB excess loss, right? So that includes all the losses. And again, when we spec our lasers, we spec it into the waveguide. That includes a few tenths of a dB loss there. So hopefully that explains roughly the question.
All right. We'll keep rolling. This one, I think, perhaps is for Yuval. And it regards the PDK simulation models. Are they open source?
No, not necessarily. Well, I would say it like that. The foundry is the one who are providing simulation models. So how they are providing it, it's their choice. In some cases, I've seen simulation models that are, and I'm not going to speak to Tower specifically here, but I've seen in some cases where simulation models can be encrypted, and in some other cases that they are not. It all depends on what the foundry is choosing to do.
Okay. Here's one more on the PDK. The laser comes as P-cell as well. Is the wavelength adjustable?
You want me to take that, Yuval?
Yeah.
Yes, please. Yes, please.
Yeah, we have is the wavelength adjustable? Yes, but we've designed, for instance, the DR is designed around a particular wavelength, and it's designed to be put there. It's going to be the best performance there. You can tune it if you like. And if you're in a non-datacom application for the DWDM, we have optimized EPIs for the wavelengths. So it is designed for a particular wavelength in general. And the DFBs in particular, those will be a single wavelength.
Yeah. And the component, when it comes to the PDK, comes with all those parameters built in. So it's whatever they provide, we can basically display and use for simulation later on.
Right.
Tom, are the lasers uncooled?
Yeah, currently they do operate uncooled. We designed the tunable, and we are designing the DFB for 0 to 70 for datacom. That's what we were targeting, just like any indium phosphide laser. Yeah.
Okay. What type of material is used for the integrated laser? And I think you just answered this, the wavelengths of operation.
Yeah, our PDK currently covers O band. We do have C band on the roadmap. It's indium phosphide is our tool of choice. So we're bonding EPIs of indium phosphide down on the silicon, and based on indium phosphide, we're making lasers, modulators, detectors, high-speed detectors, optical amplifiers. So it's all indium phosphide today.
Okay, so here's another one, which is going to be quite technical. Knowing that there are VGC or V-Grove or inverse tapering, et cetera, as the interface to the external world from the PIC, is there any other method or IP for the interface between the PIC directly to the PCB embedded waveguides? And here the example might be the MWIZ project at COBO.
We're open to looking at anything, and I would say between Tower and us, we can look at if there's a business, opportunity. We'll look at it. What we have today, I may have mentioned in passing. You're talking about the I/O from the PIC to the rest of the world, right?
Yeah, I think that's what the question is.
And indeed, if that's the query, again, what we have today in our PDK is we have a surface normal coupling, and so it's kind of like a VCSEL, right? And we also have edge coupling, and then we have it going in the same direction where the components are. Generally, that's used for wafer level test. That's what we have today. And again, if there's another one, you can approach us and talk to us, or you can work with Tower. We're open to however you need to get the light off the chip. We don't have that on the PDK today.
Okay, so our Q&A is rolling right along. We've got a whole bunch of them coming in, so we'll try to go as quickly as possible to get through as many as we can. Tom, could you elaborate on the organic substrate? Do you have partnerships in place for that?
We know some partners. Again, there is an ecosystem around our technology, just like anybody, any chip or licensed player. Again, we don't endorse any particular ones, but we do know some, so we can happily connect you with them. But we don't have any we don't prefer or anything like that. So whether you use ASE or Kyocera or anybody or Nanya, you use what you want to use. If you need some help, we'll try to connect you, of course.
Great. Tom, what do you think? Is this suitable for chiplet applications such as UCIe? Thinking about rack-to-rack connectivity under 10 meters for PCIe and CXL.
Yeah, I do believe it's applicable for that. People talk about it for those applications. First of all, we're going to be the smallest, lowest power, and ultimately the lowest cost in volume and scale. People do, to be fair, people talk about the external laser, and the primary reason they do that is in order to separate the temperature requirements of the laser. If you want to do that, or on board, you have a little more thermal work to do, but you will end up with a lower power solution. Yes, we do believe that it would be applicable there, and we're actually excited to see and to explore that with our customers and make sure we have the PDK and components. We believe the datacom components are very close to what you need for CPO, again, cost, power, right? And but we will be looking very closely to ensure that anything else, different IOs or anything like that, that we do develop that in our PDK. And that is, again, our purpose for being here. You go to Tower and you go happily tape out parts. We're here to develop the roadmap to make sure that we have higher speeds, enable COBO, enable LiDAR, et cetera.
Okay. So Tom, you've already talked about yield and that you're satisfied with what you've been seeing, but just for clarification, would you say that you're in production now?
What would I say?
Production.
I would say we are production ready. We are not in volume today, but we are ready to go to volume.
Okay.
We expect volume to start next year. It's all about the design cycle. It's, the usual module quals, et cetera, but we expect that to start next year, the volume ramp. And again, together with Tower, I've talked to the folks there and we actually feel quite good about it.
Okay. So this one, perhaps Yuval or maybe back to Tom, foundry and tool support and development is great progress. That's certainly true. Could you comment on whether there's wafer and IC test equipment availability for this? Is the test and quality assurance players and manufacturers engaged at this point like you'd like them to be?
As far as the ecosystem for test,
yeah,
such.
Right, exactly. When it's coming out of the fab, is there the test equipment and quality assurance and all the other things that you would need at scale? How far along are those guys?
Yeah, I think it is in place. Again, kudos to the others who have tread ground before us, both the other company that's doing the integrated lasers, but also the standard silicon photonics. If once the wafer comes out and you need to dice it and grind it and do all that fun stuff, there's a healthy ecosystem, bumping, grinding, and all of that. As far as test, we can help customers with that if they need it. Again, the equipment and the infrastructure is very standard. We are a bit unique because we do have the laser, we have modulators, and we can do some interesting things like actually test at speed at wafer level. And that's a little bit new and unique. And we can help customers to take advantage of that. But it's adding on to something that's already there. So I do feel like the infrastructure is in place.
Yuval, what about you?
I will say that at least from the tool side, so I can't comment too much on whether manufacturing has everything in the ecosystem because I don't know. But I'm sure they are because it is a business that is, people are shipping. I see a lot of development happening. People are shipping great deal of PIC products out there already. We've seen it in publication everywhere. So I never heard a concern there. What I can tell you that on the tool side, be able to collect the statistics from the foundries, and the foundries are collecting those statistics to create some statistical models so people can do better predictability on yield and things like that. This is something that is actually happening. We are working with OpenLight, we're working with the foundries on enabling all those capabilities like Monte Carlo and things like that. So engineers can get a higher confidence of what they will get at the end of the day from yield point of view.
Okay. So we have just a couple of minutes left here. Tom, looking ahead at where this is going, there's a question on the max power achievable with hybrid lasers. How do you think that could play out in the future?
As far as the maximum power, first of all, I thought maybe we moved too fast. We left too much time for Q&A, but I'm glad we had a little extra time for that. So as far as power, we're getting the most push for high power coming from the LiDAR customers. They seem to be wanting 100 milliwatts or 200 milliwatts. We have some ways we believe that we can meet those requirements. And so essentially it is an indium phosphide component. It's no different if it's bonded and processed on top of a laser or not. Think of it as whatever you can get out of a SOA. We can get. The advantage, however, is that we can combine elements and make very large numbers of lanes. So we can do some cool things that you can't do with discrete devices. So we actually feel pretty good there, but we're working on that.
And are there any constraints that you would see in bonding of indium phosphide the hermetic packaging, temperature constraints, those kind of things?
It has the same temperature constraints as any indium phosphide laser. It's the same stuff. And silicon's actually a pretty good medium. Our thermals are quite good. As far as limitations, sorry, what was the other part of the question?
In the packaging, yeah.
It actually acts like a hermetic. The way it's coded, you actually don't have an open facet like you do on a discrete laser. So you don't need to hermetically seal, which is nice. And as frankly, Intel has shown, there's some very good reliability that you can get from a platform that's analogous to that. And so, no, we're actually not too concerned. Actually, we feel it's a bit of an advantage. As far as the bonding, it is a very high yield process. We're actually very good there. That's in the 99% type side. So that's actually works quite well. That's not one of our limitations.
Okay. And I just wanted to get back to Jeff here, right at the end, and ask you, Jeff, for some more perspective on the data center side, where do you see this going?
The data center side. Well, the data center folk are keenly interested, as I said earlier, in power reduction. So the key premise of the CPO, the initial focus was for total power reduction of the system. So I think the main thing here is we need to keep tracking power reduction and across these technology platforms and integration methods, and really keep track of what's going to achieve the goal. I'm sure Tom can speak to integration of technologies in a CPO module as well. So there's different form factors. The key thing now is really putting our finger on what is going to be best for total power reduction. The concern with CPO was having an external laser source for in-field repair in case of laser failure. But there are other ways of managing reliability and so on.
All right. So we are at the top of the hour. I think Tom had you'd said something about it all comes down to scale, power, speed, and cost.
Yeah, that's what we believe.
Yeah. So want to thank our panelists for joining us today. This has been a really interesting session here, and I think we've gone through most of the questions, not all of them, but we certainly have those questions written down, and we'll get back to the audience members if we didn't answer your question. We'll also make this presentation available, for on-demand viewing. I think that will get posted probably in about a week to 10 days, along with the slides. So with that, I'd like to thank everybody for joining us here today. Thank you, Tom. Thank you, Yuval. Thank you, Jeff. And thank you to our sponsors, the DuPont Silicon Valley Technology Center. So with that, have a great day.